All right, here's problem 49 on page 328 of your book. It says we've got a uniform disk. So here's our uniform disk of radius r and mass m is free to rotate on a frictionless pivot through a point on its rim. And here it is. Here's the pivot point right there. If the disk is released from rest in the position shown by the blue circle, what is the speed of its center of mass when the disk reaches the position indicated by the dashed circle? So we're going to release this disk, and it's going to swing down, pivoting around here. And we want to know how fast is it going, right here. What is the speed of the lowest point on the disk in the dashed position? So we want to know the speed of this. Now I can just tell you it's going to be twice what this one is. This one's going to be twice as big because it's twice as far away from the pivot point. And then part C, repeat part A, that is the velocity of the center mass, but when it's a uniform hoop instead of a uniform disk. So let's do part A. Now, I always want to use energy if possible. Whenever they ask you for a velocity at the end, either a linear velocity or an angular velocity, you have a state at the beginning, and if gravity's doing work or something, try to use. Usually, energy is easier than using kinematics. So that's what I'm going to do. I'm going to notice that, look, the center of mass of this thing is at this level, but then the center of mass of the disk is here. So it's like the whole thing moved down by that much. Thank you. So we're going to set up an energy equation, and we're going to say that the initial energy equals the final mechanical energy. And I can do this because the only force doing work here is the force of gravity. And so initially, let's call this right here, we'll say that U equals 0 at this point. So its initial energy was all gravitational potential. So that's going to be mgh, but h in this case is r. So mgr is the gravitational potential energy of this disk when it's in this position. If we say that zero potential energy is right here. All that turns into rotational kinetic energy when it's here, because it's swinging about this axis, and that's 1/2 I omega squared. But we have to figure out what I is. So, well, anyway, we can solve for, let's just go ahead and solve for omega, and then we'll multiply by r to get the velocity. So omega is equal to 2 mgr divided by I, and we'll take the square root of all that. Now we have to figure out what I is. Hey, on the exam, there's a problem where you have to use the parallel axis theorem. Make sure you don't forget about that. I equals I about the center of mass plus md squared, where d is the distance from the center of mass to the axis of rotation. In this case, we moved the axis of rotation from the center out here, which is just r, so d is r. So now this is a uniform disk, so I about the center of mass is 1/2 mr squared, and I should use capital M, plus capital Mr squared. So we have 1/2 an mr squared plus an mr squared. So the total rotational inertia of that is 3/2 mr squared. So we're going to put that in here. So the angular velocity at the bottom is going to be the square root of 2mgr over 3/2 mr squared. And we can see that the mass cancels, one of the r cancels. Now here we have 3/2, let's reciprocate and multiply. We have 4. 2 times 2 is 4. Square root of 4 is 2. Times the square root of g over 3r. Did I leave anything out? I think everything's good. And that's dimensionally correct. This is meters per second squared. This is meters. So the meters cancel out. You get per second squared. You take the square root of that, and you get per seconds, which is really radians per second. Now all I have to do now to figure out what the velocity at the center of mass is say, well, the center of mass, how far away from the axis of rotation is it? Well, it's r. So that's going to be r omega. And r omega is, well, we'll just multiply this by 2. So it's 2r times the square root of g over 3r. Now, this isn't really simplified as much as it could be. Let's put an r inside. This is as if you have 2 times the square root of 2r squared. I'm sorry. We'll put that in the radical by calling this r squared g over 3r. And so now I can cancel this r with that. So I've got 2 times the square root of rg over 3. And that's the velocity of my center of mass. Is that correct? That's right. Okay. Now for part B, the velocity at the lowest point here, that's just going to be twice as big. Because instead of r, we have 2r. From here down to here is 2r times omega. So that when I do, I just get 4 times the square root of rg over 3. So that's part B. I'm not even going to show any work. Just explain it. Okay. Now, if we have for part C, the velocity of the center of mass for a uniform hoop, all we're doing is changing the rotational inertia of it. So here's the parallel axis theorem again. Well, what is the rotational inertia for a hoop? It's mr squared plus, and then this is just going to be mr squared. So I is just going to be 2 mr squared. And so that's what we're going to substitute in here for omega. And actually, yeah, we'll just do that. It's 2 mgr over 2 mr squared. So once again, a lot of stuff cancels here. And we're just left with the square root of g over r. Now we multiply that by r to get, so the velocity of the center of mass is going to be r omega. So that's going to be r times the square root of g over r. And again, we'll do the same trick we did before. We'll place that r in the radical. And we get the velocity of the center of mass is the square root of rg. Is that correct? Is that okay? Darius, is this right?
Yeah.
Okay. Okay.
When you multiply the R in, that's what I was getting.
Yeah.
That's how to simplify it.
Okay. So here's the whole problem. And one of the key things is please don't forget about the, like, hey, on the test, I'll give you the formula for the I for the center of mass, but I'm not going to give you the parallel axis theorem. You're going to have to remember, if I shift, I do, and there's a problem where I shift the axis of rotation to a different place, and so you'll have to use the parallel axis theorem. So just remember that. And also conservation of energy applies just like it did with linear motion. Okay, that is all.